In this video, we are going to look at logarithmic functions, often just called logs. So what logarithmic functions are is they're actually the inverses of exponential functions. So think about it as addition and subtraction. We use addition to get rid of subtraction and vice versa. The same thing with division and multiplication. We use these two operations to kind of undo one another, and that is exactly what we do with logs and exponentials. So logarithmic functions can look like f of x is equal to log base b of x, so this would be function notation, or y equals log base b of x. So I want to show you the difference. We're going to talk about how to turn our log functions into exponentials so it's easier to work with them. So before we were talking about exponentials, and we defined an exponential function as y equals b to the x. So we can turn a log into an exponential, but what's going to be different here is it's going to be x is equal to b to the y. So in an exponential function, x is the exponent. That's what we're plugging in. And in a log, y is the exponent. That's what we're plugging in for. So we can take all logs and we can rewrite them in this form. So basically the only difference between the exponential form and the log form is that we have switched the x and the y, which means we've also switched the domain and the range. So remember, for exponential functions, our domain was unrestricted and our range was 0 to infinity. Well, since domain represents the x values and range represents the y values, and we're just switching x and y in the equation, now this is going to have a domain of 0 to infinity, our log functions, and a range of negative infinity to infinity. Okay, so we're going to work on rewriting exponentials as logs and vice versa. So the first one we're going to look at, the first example, is 3 to the 4th is equal to 81. So right now, this is b to the y equals x. And remember that our log form is y equals log base b of x. So we're just going to move these three values around so that they're in this form right here. So y is 4, so 4 is equal to log. Notice that the base of the exponential and the base of the log are the same, 3 of 81. So log base 3 of 81 is equal to 4. Next, let's look at 10 to the 3rd is equal to 1,000. So again, this is b to the y is equal to x, and we're going to put it in log form. So 3 is equal to log base 10 of 1,000. Now, one thing I want to note is that normally when we have a base of 10, we don't write that one because it's one of those things that's understood. So we would write this 3 equals log of 1,000. So anytime you don't have a base given, you are to assume that it's 10. Let's look at e to the 0 is equal to 1. So this one's going to be slightly different because we have a base of e. So right now we have b to the y equals x. Now anytime we have base e, instead of using log, we have to use ln for natural log. And there's also a separate calculator button for that. So to rewrite this one, we would have y, which is 0, is equal to natural log base e of 1. And just like with the last one, if we have natural log, we know the base is going to be e. So we don't actually have to write that. We can just write 0 equals natural log of 1. Okay, so now we're going to go the other way, and we are going to turn logs into exponentials. So remember, we're going to go from log base b of x, we can say y equals over here, and we're going to go from that to b to the y equals x. So our first example, let's look at log base 3 of 81 equals 4. So we're going to rewrite this. This is b, this is x, and this is y. So this will become 3 to the 4th is equal to 81. And you can actually check that one or just look at it and see if it makes sense. Is 3 to the 4th power 81? And it is. Next, let's look at log base 7 of 1/49 is equal to -2. So again, this is b, this is x, this is y. So we'd rewrite that 7 to the -2nd is equal to 1/49. And again, we can see, okay, that makes sense. 7 to the -2nd power would mean it's a fraction. We'd flip it over, and 7 squared is 49. Now, let's just say you're given an expression like this. You're asked to figure out log base 3 of 9. So now we don't have anything that it's equal to. Well, if we want to, we can go ahead and add in equals, and then over here would be y. So you can go ahead and add that in, and then we can figure this out by simply rewriting it. So we would rewrite this. Again, this is b, this is x, and we know that this is y. So 3 to the y is equal to 9. And then we can easily figure out that y has to be 2 because 3 squared is 9. So log base 3 of 9 is equal to 2. Let's look at another one. This time, let's look at log base b of 5 is equal to 1. So this is b, this is x, and this is y. So let's rewrite this. B to the 1st power is equal to 5. So we know in order for that to be true that b has to be 5 because 5 to the 1st power is equal to 5. Okay, next let's look at log base 2 of 2 to the 4th. Again, we don't have anything it's equal to, so we can say is equal to y. So this is b, this whole thing is x, and that's y. So 2 to the y equals 2 to the 4th. And again, in order for those two expressions to be equal to each other, y has to be equal to 4. Next one, Let's look at log base 4 of 1. So let's set that equal to y. So this is b and this is x, and we'll rewrite it. 4 to the y is equal to 1. So in order for that to equal 1, we know this has to be a 0 exponent. So that is all equal to 0. Now let's look at an exponential that has a log in it. We'll see these sometimes. So let's say we were given 3, and then our whole exponent is log base 3 of 4. So again, we can add in the equals y over here. So this is our base. This is actually our exponent y. So let's go ahead and call this one x instead. So when we're rewriting this now as a log, because remember we're starting with an exponential, we will have log base 3 of x is equal to y, and y is log base 3 of 4. That whole thing is y. So in order for these two expressions to be equal, x has to be 4. Let's look at one more example like that. Let's look at log base 125 of 5 is equal to x. So let's start by rewriting this. We have 125 to the x power is equal to 5. So we have to think about, how do we get from 125 to 5 by using an exponent? We have to somehow make this smaller. We know a negative exponent won't make it smaller, so we need something like a cube root. We know that the cube root of 125 is 5. So this would be 125 to the 1/3 power. Remember, that's the same as the cube root. So x is equal to 1/3. So anytime you're raising a bigger number to a power and getting a smaller number, you're either using a negative exponent or a rational exponent. Okay, so let's talk about how to graph logs. The first thing we want to do, if we think about this as y equals log base 2 of x, we want to always start by writing this as an exponential. So 2 to the y is equal to x. So just like we talked about before, notice y is now the exponent. So I want to plug in for the exponent. So I'm going to choose y values. So this is one of the very few times that instead of choosing x values, we're going to actually choose y values. So I'm going to make a table here, just like we always do. And this time I'm going to choose y values of -2, -1, 0, 1, and 2. And we're going to go ahead and plug those in. So 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1st is 2. And 2 squared is 4. So these values should look very familiar because they're actually the same as y equals 2 to the x with the x and y switched. So now we can go ahead and we can graph these on our coordinate plane over here. So we're going to start with 1/4, so I'm going to go over just a little bit, 1/4, and then down -2. I'm going to go over a half and down 1. I'm going to go over 1 and up 0. I'm going to go over 2 and up 1, and then I'm going to go over 4 and up 2. So now, instead of having that horizontal asymptote, I'm actually going to have a vertical asymptote. So the vertical asymptote is going to be at the y-axis. So this is a vertical asymptote at x is equal to 0. So my graph is never going to cross or touch that line like we talked about earlier. This means I have restrictions on my domain. My graph starts at 0 and heads toward infinity. And then with my range, again, we could pick anything we wanted, so we have a range of -infinity to infinity. Here's a second example of graphing a log function. So again, I want to think about this as y. So I'm going to rewrite this as 1/3 to the y is equal to x. And just like we did in the last one, because y is the exponent, I'm going to go ahead and I'm going to choose y values again. And I'm going to choose -2, -1, 0, 1, and 2. And I'm going to go ahead and plug those in. So 1/3 to the -2 means we flip that fraction over. So 3 squared is equal to 9. And then 1/3 to the -1st, flip the fraction over, that's 3 to the 1st, which is 3. And then we have 1/3 to the 0, which is 1. We have 1/3 to the 1st, which is 1/3. And 1/3 squared, which is 1/9. So now we can go ahead and plot these points. So we're going to go over 9 and down 2. We're going to go over 3 and down 1. We're going to go over 1 and up 0. We're going to go over 1/3 and up 1, and then 1/9 and up 2. So again, we have this vertical asymptote right here. But now that I have this fraction base, instead of my graph increasing, it is decreasing, just like we talked about with exponential functions. If this is less than 1, our graph should be decreasing. But we still have a restricted domain starting at 0 and going to infinity. And then our range is -infinity to infinity. So this next graph has a transformation. So our parent function down here, I just copied the table over from what we did before, was x is equal to 2 to the y. So remember that's log base 2 of x is equal to y, and we just convert it to our exponential form. So we're going to start with that parent function. And then this -1 is grouped inside parentheses with the x. So this is a left or right transformation. Because that's a minus sign, it means it's going to shift everything to the right one. So let's graph our parent function first. So 1/4 -2, 1/2 -1, 1 0, 2 1, and 4 2. So here was our original vertical asymptote, and this is our parent function. It's increasing. So now all we're going to do is move each of those points to the right one, which means our asymptote is also going to shift to the right one. And then we'll just move all those other points over 1, and here is our new graph. So now this is x equals 1. We start at 1 and we head toward infinity for our domain, and our range stays unrestricted, negative infinity to infinity. Okay, now we're going to look at the graph of natural log of x. So we talked about this briefly earlier. Remember, if you have natural log, you know that the base is e. So we're looking at y equals natural log base e of x. And the first thing we want to do is rewrite this as an exponential. So e to the y is equal to x. So again, just like in all the previous graphs, y is our exponent, so we're going to choose y values of -2, -1, 0, 1, and 2. And remember, you'll need your calculator to plug these in. So for the first one, we'll have e to the -2nd, which is about 0.1. And then we'll have e to the -1st, which is about 0.4. And then we'll have e to the 0, which is just 1. E to the 1st, which is about 2.7. And then e squared, which is about 7.4. And now we can just go ahead and plot those points. So we'll go over 0.1, which is like barely going over, and then down 2. 0.4 is about half, and then down 1. 1, 0. 2.7, so close to 3, and then up 1. And then 7.4, so almost halfway between 7 and 8, and then up 2. So here is our vertical asymptote, and our graph is increasing because we have a base of e, which remember is about 2.7. That's larger than 1, so our graph is increasing. Again, this is x equals 0, so we're headed toward infinity for our domain, same as our other function, 0 to infinity. And then our range is just -infinity to infinity.